Hi, my name is Matthew Castronuovo, and this is my lab report for Lab 1 Constant Velocity. So, a brief intro into my lab. The purpose of my lab is to observe the velocity, position, and acceleration of an object in motion. This object being a cart that I pushed on a track, and we are going to observe how it moves during its travel. Important concepts that will be talked about in the lab, the first of which being Newton's first law, which means that an object in motion is going to stay in motion, and an object in rest is going to stay at rest unless that object is going to be affected by an outside force. And Newton's second law states that force equals mass times acceleration, and acceleration is going to be the difference in velocity over the difference in time. You're going to observe how this affects the cart in the real world as opposed to in our computation. And the position update formula shown on the right of the screen is going to be position final equals initial position plus average velocity times the difference in time. That's going to be the basis of my computational model. And then the force of friction and air resistance that move in opposition to the car's motion, these forces are going to cause a deceleration in the positive x direction or an acceleration in the negative x direction. I'm which way you look at it. And then the main results of my lab are shown in the top right of your screen, and it's going to be this position time graph with the blue dots being the observed values that were found, and the orange line going to be the computational model. So the system of this experiment was the cart that was being pushed, and the surroundings are all objects touching the cart that are playing a role in its movement, or even just anything that comes into contact with the cart. So the tracks the cart is on, the air around the cart, any dust that might have blown onto the cart, anything at all that is not the cart is going to be considered surroundings for the purposes of this lab. And the experiment details are going to be that I pushed a cart and captured its motion along a track with a video, and then used the app tracker to calculate its position along a line during its motion. So the model that I developed, it took in several key assumptions, one of which is that the car is moving linearly on only the x-axis. It is not moving with any y direction or z direction. Its motion is purely on the x-axis. And furthermore, no forces are acting on the car in the x direction. This is an assumption that you will see causes some deviation with reality, but it makes the computational model a lot more easy to comprehend. So the key components of my coding, in line 36 and 37, I input the initial position and velocity of the car. So its initial position was 11.89 centimeters, and its initial velocity was found, or rather, its initial and constant velocity was found by taking the first two observed points of the car. So its initial position minus the next point that the car is observed at, minus the delta time that it took for that car to move that next position. This is the velocity that is the vector of velocity that is staying constant throughout the whole experiment in this model. And then during the while loop, the position update formula was utilized in line 61 to update the ball's position in the model in a linear fashion using the constant velocity that we have and the updating position of the ball. So the model gave us the orange line that you can see on this graph, and it did so by taking the 2 points, finding the slope between them, which is the velocity, and extrapolating out, giving no deviations in this velocity. And then the blue dots are going to be our observed data that was taken on tracker. So as you can see, it looks to be a very accurate model, but down towards the end, you can see there is a deviation between the blue and orange. Now, why is that? Well, first of all, we need to take a look at our model's assumptions. We assume that no forces are acting on the object in the x direction, and we assume that no human errors were made. Possible human errors could include errors in my push. I might have somehow impeded its progress at some point. There might have been some bumps on the track that weren't taken account of. Furthermore, when I input the data on tracker, I could have done so wrong. These are possible human errors that were not accounted for. So what if we flip the x-axis? Well, flipping the x-axis does not change the magnitude of the velocity vector. It only changes the direction. Remember, a vector has magnitude and direction. And by flipping the x direction, we're simply just flipping the direction of the vector from positive x to negative x. What does it mean? Can we determine the sum of all the forces acting on our object? Well, yes and no. In the y direction, we see that there's no movement, even though there is a force or multiple forces acting on the object. Those being the force of gravity pushing down and the normal force pushing up. Now, because we see that the object has not moved in the y direction, we conclude that the sum of all the forces in the y direction is zero. However, in the x direction, because there's a difference in velocity that we observe, we know that there is going to be a non-zero sum of net force on the object in the x direction, and that is going to be given by the force of friction and air resistance. How do we know this? Because our model was an overestimate, and our observed values were under the model, meaning that it was decelerating by a small margin.